Okay, so welcome to this next video in which we are discussing entropy and the second law of thermodynamics. Okay, so we're at the exciting bit now. We've seen how our hypothesis that the criterion for a chemical reaction to occur is that the energy of the products is lower than the energy of the reactants fails. Okay, so it's wrong. So we need to go back to the drawing board, and the concept that we're going to develop is the concept of entropy. Okay, and I think the most helpful thing to think about if you want to understand entropy is to think about dropping a drop of red dye into a glass of water. People often start by saying, oh, entropy is disorder, but I don't think that's a very helpful comment at all, really, because they don't expand on that at all. So we're going to give a different definition of entropy. We're going to give the proper definition of entropy, rather than just calling it disorder. Okay, so let's think about what happens when we take a glass of water and we're going to drop a drop of red dye into it. Okay, so here is our beaker of water. Now let's colour in all the water molecules. Well, let's think about what the water actually is. Now we'll just imagine that the water actually just consists of water molecules. Of course, normal water does not just consist of water molecules. There are things dissolved in it. But we'll, just for simplicity, think of this as a thing of water molecules. And we'll colour in the water molecules in blue here. Okay, so each one of these dots represents a water molecule, and of course you will have billions upon billions, billions of billions of billions of the things, okay? Well, billions of billions at least, maybe not billions of billions of billions, but you'll have billions of billions of the things. So you will have a lot of water molecules in this beaker. Okay, now what have you done? You have put in a drop of a drop of red dye molecules. So let's say initially they are all together as a dot, basically. Okay, so here are all the red dye molecules. Now the question is, do they remain like that? Well, the answer is no. If you leave that now for a few hours, or however long it will take, it will happen much quicker than that, but leave it for a good deal of time and come back, what will you find? Well, you will find something that instead looks like this. Okay, so here is our beaker again, and let's again go through the process of putting in all our water molecules. So all of these blue dots are water molecules, okay, in our beaker, and I'll have to draw a similar number to previously, so I'll make sure the picture's good, so I'll invest a little bit of time into it. Okay, so there are our water molecules, and now let's put the red dye molecules. Well, of course, they will have spaced themselves out, and you'll end up with a much less intense dot of red, basically. So the whole thing might appear slightly red now, and the molecules will be spaced out, basically, like so. So the question is why? And a better question, an even better question than that, is, would you ever, ever, ever take this flask, which has the water molecules and the red dye molecules interdispersed among, homogeneously, would you ever, ever, ever see it go back to this? Would you ever see all of the red molecules just go back to the same space up here and form a droplet again? Well, the answer is, of course, no. And if you want to understand entropy, think about that. Why? Why do you not see the reverse? Why do you not suddenly see all of these red molecules clustered again into a droplet after they have dispersed? Okay, so let's answer this question now. Why do you not see them? Well, it's because, effectively, all of the water molecules and all of the red dye molecules, they are positioned randomly, okay? And the chance that they're all just going to aggregate up there again, all of the red dye molecules are just going to happen to re-aggregate up here. The chance of that is really small. Okay, now before we go any further, I want to introduce you to some terminology. Okay, I want to introduce you to the terminology microstate and macrostate, because this will be really helpful when we're defining entropy and understanding entropy. Okay, so what is the difference between a macrostate and a microstate? Well, basically, a macrostate is something that a human can observe. When you look around the world, you do not see water molecules. You do not see red dye molecules. What you would actually see if you were doing this experiment, you would see a beaker of water, okay, with a drop of red dye in, okay? This is the macrostate, the state that you, as a human being, can actually observe. Okay, so this is the macrostate. The microstate means if you were a tiny little molecule yourself and could see the other molecules, what would you see? So this picture that I have drawn here of all of the water molecules with all of the red dye molecules, this is the microstate. Okay, we cannot see that. We cannot see water molecules. We cannot see red dye molecules. All we see is a red dye droplet and water surrounding that. And that's a really, really important distinction between what we see and what we measure, which are the macrostates, and what is actually there, which is the microstate. Okay, so we are trying to justify why does a macrostate, and let's draw the macrostate for this, because we've got the microstate here. The macrostate is, of course, that you end up with a sort of less intense red, basically. You sort of end up with maybe a sort of, it's sort of interdispersed among the water, so you sort of end up with a mildly red solution here, okay? Right, so that's the macrostate, that we've now got a beaker of fluid that is sort of like a very faint pink. Okay, what we are asking is, why does this macrostate, why does my beaker of water that is a faint pink not return to clear water with a very intense red drop in it? That is the question we are asking. And basically, the answer is that the probability of this occurring, if you're just randomly positioning red dye molecules and water molecules, the probability that you will actually just happen to position all of the red dye molecules so that they're clustered up into one area, that probability is tiny. Okay, now let's explore that a bit more. Why is it so tiny? Okay. So basically, we are positioning water molecules and red dye molecules, okay? And there are loads of different ways that we can arrange all the water molecules. We have an absolutely huge number of water molecules in here. Let's say big N represents the number of water molecules we have. And then we have, let's say, big M represents the number of red dye molecules. So I'll just colour them in. Then the actual number of ways that you can position all of the little blue molecules, all of the water molecules amongst all of the red molecules, the number of ways you can rearrange that is enormous, basically. Okay, now there are a huge number, therefore, of different microstates. There are a huge number of different ways that you can arrange all of these blue molecules and all of these red molecules. Now let me just try and explain what I mean to you by that with a simpler example. Okay, so let's make a simpler model of what we're trying to do here. Okay, so a nice simple model for what we're doing is we could model space as being finite, or discrete rather. Okay, so we could model the beaker as being made up of 16 squares, if you like. Okay, like so. Okay, so we've got these 16 squares that make up our beaker. So I'm just sort of like, I'm trying to make you understand what I mean by all of the plausible microstates that this system could exist in. And to do that, I'm making a simpler model of it, basically. So let's say in this beaker we have 5 blue molecules, okay? And let's say the blue molecules occupy all of the square, okay? Like so. So one way that we could set this up is we could put them in these 3 squares, and then we could put the 2 other blue molecules here, and I'm just making this up basically. Okay, and then 1 there. And let's say we have 1 red dye molecule, and let's choose to put it there. So basically what I mean by all the microstates of this system is every possible way you could do this. So you have 5 blue molecules to put in, so 5 squares that you can fill in blue and 1 square that you can fill in red. Okay, so how many ways could you do that? Well, there's absolutely loads of them. Let me draw another one out for you. Okay, like so. So here's our beaker of 4 squares, and I want to stress that I'm just doing this to try and get the concept across. It's obviously a very oversimplified model of our beaker. Okay, but this time I could put the blue molecule here, another blue one here, another one here, another one here, another one here, and then where can I put the red dye? Maybe I'll put it in the same square, but this is a different microstate. So all of the different positionings of the water molecules and the red molecules, those are all of the possible microstates. So this system has an absolutely huge number of microstates. This is what I mean by microstates. And you have to go through every last water molecule and tell me exactly where it is in the beaker. You also have to do that for every last red molecule. That completely specifies the microstate. There are absolutely a huge number of microstates. Okay, so let's now try and explain why you never see a faintly pink liquid where the red dye molecules are interdispersed homogeneously, returning to a transparent water fluid liquid with a red dye drop at one point. Okay, so what do we mean by the probability of this is very low? Because it could happen. There are microstates that correspond to that. Now my question is there only one microstate that corresponds to that? Well, no. You know, I could switch this blue molecule with this blue molecule. That would be a different microstate, basically. But it would look exactly the same. There are loads of different microstates. You know, I could move a few of these around a bit and it would still appear as the same macrostate. So if we take a macrostate, which is what we as humans can see, such as a red droplet being in this water, there are a huge number of microstates that would all look like this. Now, basically, if all of the microstates are equally likely, let's assume that all of the microstates are equally likely. So if you specify an individual microstate, i.e. you go through every single water molecule and tell me exactly where it's positioned, you go through every red dye molecule and tell me exactly where it's positioned, each one of those is equally likely. There's no one microstate that's more likely than the others. Okay, but when we talk about macrostates, then it's different, because the number of microstates that would all look like this macrostate. So if you take a microstate and look at it as a human now rather than as a molecule, what would it look like? Well, basically, there's a huge number of microstates that would all look like this. But compared to the number of microstates that would all look like this to a human, okay, so compared to the number of microstates which would all give this as a macrostate, the number of microstates that would give this as a macrostate is tiny. And that is the reason that you never see this going back to that. So let's discuss this again. Okay, so basically the reason you never see this going back to this is because the number of microstates, i.e. the number of ways that you can set up all of the water molecules in position and set up all of the red dye molecules in position, that then if you looked at it as a human, okay, would look like this, is far greater than the number of microstates that if you looked at it as a human would look like this. Okay, so that means that just the probability of the microstate of the system having a macrostate that looks like this is much lower than the probability that the microstate of the system will have a macrostate that looks like this, just because there are so many more microstates which give a macrostate that looks like this rather than this. Okay, so that really is the concept of entropy. The concept of entropy, then, you take a entropy is a concept associated with macrostates, not microstates. So basically you take this macrostate here, the macrostate where you have one red droplet with the transparent water around it. Okay, and you can say, what is the entropy of this macrostate? So entropy is it's a concept that's associated with macrostates, and that's important to understand. It's not a concept that's associated with microstates. Entropy of a macrostate. Okay, what it means basically is the number of microstates which, if you looked at them as a human, i.e. if you look at what their macrostate looks like, would look like this. So the number of microstates that would give a macrostate that looks like this, basically, that would give this as a macrostate. Number of microstates which would give this as a macrostate, which would have this as a macrostate, which would have this as a macrostate. That is the best way that I can explain entropy to you as a macrostate. Okay, so basically this macrostate here, where we have all of the red dye molecules clustered together in a droplet, and then the water is all clear and just pure water molecules, this has a certain entropy value, which is the number of microstates which would all look like this to a human. So all of the different ways that you could position every last water molecule and every last red dye molecule that would look like this to a human, basically. That's the entropy of that macrostate. Okay? Then this also has a certain entropy. This faint pinky fluid, the entropy of this macrostate is the number of microstates. Okay, so again, the number of ways that you could reposition all the water molecules and all of the red dye molecules that would look like this to a human, basically. So even though they're all different microstates, they all look like this to a human, and therefore all have the same macrostate. Okay, and basically the entropy for this, the number of microstates which would all look like this to a human, is much bigger than the number of microstates that would all look like this to a human. Okay, so basically it's given the symbol S. So basically, in principle, at least, you could work out what the entropy of this macrostate was. So you'd call this the S value for this. Okay, and it would be some enormous number, which is the number of microstates of the system that would all look like this to a human, that would all have this as their macrostate appearance. And again, you could work out the entropy of this macrostate here. And the reason you never... so if I call this entropy 1 and this entropy 2, the reason you never see this returning to this is that S2 will be far, far bigger than S1. Okay, so the number of microstates that all look like this are far bigger than the number of microstates that look like this to a human, and therefore the sheer probability that the system will take on one of the microstates that looks like this to a human is hugely bigger than the probability that the system will take on a microstate that looks like this to a human. And therefore you would never find it going from this to this, and you'd always find it going from this to this. Okay, so that's the concept of entropy then. In the next video we'll continue with this discussion and we'll progress to the second law of thermodynamics.